So observe the gradient on the screen from the 20 to 100 degree centigrade raceway to a sub 100 degree centigrade top. We must prevent this thermal collapse to protect our physical assets. To diagnose this, we look at furnace pulse. So coming to the diagnostic pulse of the internal heat exchange. The optic temperature is our ECG. So look at the uh, TFR formula on the right. When solid burden mass Ms increases, our gas volume Mg plummets. The TFR spikes. So these pulse hitting the danger zone signal thermal starvation. If we don't act, aerodynamic stability vanishes, leading to catastrophic channeling. So these starvation directly impact the thermal reserve zone. Coming to the survival part, as we can see the thermal reserve zone. So notice the 900 to 1000 plateau, the TRZ. It's critical for oosteite iron reduction equilibrium, as all of us know. If the gas volume is too low, represented by the narrowing red area, sensible heat is exhausted before reaching the top. You lose the thermal fuel required to dry the incoming wet burden. Why is the gas volume dropping? It's a decarbonization paradox. So coming to our modern decarbonization paradox. So follow the cycle. We inject high hydrocarbon fuels, but endothermic cracking lowers the flame, that is raft. We compensate with the aggressive oxygen enrichment, which displaces inert nitrogen. The so what is simple. Your CO2 drops, but your upward gas volume plummets, starving the top. This lack of heat failed to manage the furnace invisible water load. Coming to the moisture dynamics of the furnace. So, invisible internal load mm, looks at the slide carefully. As you can see, this uh, uh, comparison matrix. So while surface moisture is 40 kg, process water from S2 combustion add up around 65. So these combined load demands massive thermal energy. If top gas hits the dew point, evaporation fails and you are charging a wet furnace. So proper gas distribution, especially in our context, we have to take our defense first. So coming to the aerodynamic channeling part. So the role of I mean comparison these two heat maps. As you can see, the central run on the left leaves the wall cold, the wall penalty. The solution is the 20-degree peripheral ore enrichment. On the right, CFD confirm this POE forces gas flow to the periphery, ensuring the upper stack stay above the dew point. When we lose that temperature, we cross a lethal threshold. So crossing the threshold, that is the dew point collapse. So this is the danger zone. Below 100 degrees centigrade, the furnace ceases to be a dry reactor. Heavy water flashes into existence, triggering acid condensation. This liquid turns dry dust into a sticky slurry, gumming up the work. Metallurgists stop, mechanical survival begin. The first casualty is the viscous cycle within the burden. Coming to the consequences, one, the evaporation condensation cycle. So as you can see the slide of the consequences one. So follow the reflux loop, that is water evaporation deep, condenses on the cold rock, coming to the then descend to the re-evaporate, that is phase 3, shrinking lumpy zone. These loop violently push the 100-degree isotherm downward, stalling indirect reduction and forcing high cost inefficient direct reduction in the lower stack. So external system like your gas cleaning plant suffers next. So coming to our consequences too, the failure of the dry gas cleaning on the left is the optimal state. On the right, as you can see, it's a very important one on the slide display. So on the right, as you can see, this uh, very picture, which is what should be the optimal and what should be the critical, especially before reaching to the failure or arriving to the failure. So on the right, as it is shown very clearly, uh, uh, notice the here you can see the cementation part. So this subdew point vapor turns porous dust into heavy cement-like mud on the filter bag. So these blind the fabric, causing uncontrollable pressure drop and total system shutdown. So low temperature guarantee these failures. So beyond the filter, the moisture activate a chemical threat. Coming to our consequences number three. Uh, so, as you can see, the acid and chlorine corrosion cascade, and this is very important. As we know, the liquid water is a catalyst for the chlorine corrosion. So, look at the green threaded zone in the pipeline and top pressure recovery turbine. So, these precision blades are the targets. So, if you see liquid in the downcomer, you are actively losing metal and TRT efficiency to acid attack. So to fight this, we implement a layered defense architecture. And our next slide is talking about those strategic mitigation plan. So the layered defense architecture, let us talk about. So thermodynamics cannot be cheated, but they can be managed via this layered defense. So we use advanced diagnostic to see burden control to adjust and mechanical safeguard to protect. So modern iron making requires all three to overlap to maintain that critical 100 degree centigrade thermal buffer. So let's focus on the first layer, that is digital decision support. So coming to the digital adaptation part, as you can see, this slide talk about this dashboard is your early morning. The K3 indicator monitor the permeability in the real time. If your wall temperature drop, the DSS automatically adjusts chute tilting angle to redistribute the flow via slow motion. So these proactive digital shift rescue the thermal gradient before the condensation cycle even start. So when digital is not enough, we turn to mechanical intervention, and this mechanical intervention is being shared here. So as you can see, these transition moisture spikes like monsoonal pallet can overwhelm any operator. The bypass or injection loop is your firewall. So by injecting steam, we force the gas back above the dew point before it hits the baghouse. So this is not negotiable infrastructure for protecting your gas cleaning plant. So these strategies allow us to move within the iron making matrix. So coming to the most modern iron making matrix, behold uh, the roadmap. So older plants are the basically safe but inefficient. So pushing decarbonization without thermal engineering lead to the wet freeze. So success is the optimal window. You cannot increase chemical intensity without also engineering thermal stability. That is the gold standard. So mastering this gradient is the final steps. So coming to the our next slide, which is about mastering the tightrope in the tightrope. So in conclusion, we can see The low optic temperatures basically are test of our strategies, our toughness, our promptness. It is so by mastering the moisture dynamics, burden distribution, and mechanical safeguard, we secure both the hearth efficiency and the plant integrity, as well as at the same time we also display addresses our promptness, discipline, SOP concreteness in place. So the tightrope is thinner, but our tools are better. So let's back to the work.